Hi there. I just wanted to finish up where we left off yesterday in the lecture because we had a couple of slides that we didn't quite get to and I didn't want to rush through. So we're going to cover those today, kind of critically important to round out action potentials. And I'm backing up a slide because in my review, I realized that I misspoke. Yesterday I said milliseconds for these two units, and they should be meters per second, which will make more sense. So the take-home message is, in an unmyelinated axon, we have a travel speed of 0.5 to 2 meters per second as a velocity. In contrast, if you myelinate this, you go 12 to 30 meters per second, much, much faster. Okay, so the milliseconds was a mistake, and I've updated that on the recording. You'll have to see a little note there, but I wanted to cover that. So let's talk about depolarization. Depolarization is a term that we use to talk about an action potential. Depolarization is a reduction in the membrane potential. And we're going to walk through this picture right here on the left. And that's going to be a picture that you're going to see a lot over the next few weeks as you're watching the lectures and studying. So it's really important that you understand this and get oriented. On this left graph, we can see that the time is on the x-axis and millivolts are actually on the y-axis. You can see 0 is right here, and minus 70 is the resting membrane potential at the level of the phospholipid bilayer, like we were talking about in lecture the other day. And the sodium-potassium ATPase pumps help to maintain this resting membrane potential. Now you can see local potentials will come in where you'll get a signal, a ligand, or a voltage that will slightly depolarize the membrane. And a local potential or a graded potential will summate or add together here in this area of stage 1. Now, once they summate and cross threshold at minus 55 millivolts, which is stage 2, it converts to an action potential from a local potential or a graded potential. This action potential is an aggressive depolarization event. As this membrane now becomes less and less negative, in fact, it crosses 0 and peaks or spikes at positive 35. So this depolarization of stage 3 ultimately will peak at stage 4 at about positive 35, and then you repolarize. You repolarize, making it, again, more negative. Stage 5, you cross the threshold spot, you go below and overshoot the minus 70 resting membrane potential. That's stage 6, and we call this hyperpolarization because hyper means too much. And then the sodium-potassium pumps help to reestablish that resting membrane potential and maintain it. And that's stage 7. So this classic signature is an electrical graph of what's happening at the membrane from minus 70 past threshold to positive 35, repolarize, back past 0, past minus 55, overshoot minus 70, and then you reestablish resting membrane potential in step 7. Now, the right side is showing you temporally how this fits in. So these are milliseconds, okay, not meters per second. This is milliseconds. And you can see that this spike or this action potential happens in very, very small number of milliseconds, really fast. And the hyperpolarization event takes 10, 20, 30, 40, 50 milliseconds for the membrane to reestablish resting membrane potential. In that state of hyperpolarization, which is the opposite of depolarization, we say that this is an inhibitory event. Now, the membrane is hyperpolarized, so another action potential won't fire. Now, we're going to unpack that a little bit more in future lectures, but here's the real reason why, just real quickly. If you have a nerve and you're going from this side over to this side, and you're firing along that nerve, you want the membrane signal of depolarization to move in this direction. So you make behind where the action potential left more negative. So the easier direction for it to go, the path of least resistance, is actually this way. So behind it, where it fired, you hyperpolarize so the signal won't go backwards. And that's the reason that you have a hyperpolarization event. It's to directionally send the electricity down the nerve. Make sense? Okay, so let's talk in these last two slides. What are the local potentials? How do they stack up or summate in this area right here to reach a threshold? So you can do this by magnitude or by temporally summating, right? So you can say, here we've got a graded potential, otherwise known as a local potential, that's depolarizing. That's the yellow hump. The green one is a hyperpolarization. So it can go in the opposite direction to make it less likely or make it inhibitory so the nerve won't fire. This graded potential is larger. We say graded because this is smaller. This is graded at a larger grade. The orange one is graded even bigger. This dotted line is resting membrane potential of -70. Or instead of having different sizes or grades of signal, you can actually time the stimulus where this event happens here. This one is larger and happens here. Or you can have two that fire side by side and then they summate to stack the signal. So if you had two signals that were firing side by side right here, you might get one that depolarizes it to here, the second one that depolarizes it to here, and then it crosses threshold and you get firing of the nerve. You don't get firing of the nerve until you cross threshold. And once it crosses threshold, it converts from a local or a graded potential to an action potential. So these local potentials are short-lived. They're local. They will dissipate or they'll go away. And that's on this next slide. They'll dissipate or go away if they're not used. If they don't reach threshold, then they fade. We call that terminology decremental or dissipation. They are reversible, right? Because you can fire them, not use them. Once you trigger an action potential, you can't reverse it. It's too late. It's actually triggered. We already said on the prior couple of slides, you can either hyperpolarize with a local or graded potential, or you can depolarize with a local or graded potential. So what are some of the initiators, or what would cause a local or graded potential to take place right in this area? And remember, on the nerve, this signature is taking place, or that signal of electricity is happening at that axon hillock, like we talked about the other day. So initiators, these could be energy, they could be heat, light, that open ion gates, that allow for ions to move, for sodium to come into the cell and make the cell less negative, right? That's the depolarization event. They could be neurotransmitters like acetylcholine that we'll learn about in later lectures. They bind to a ligand, it opens a gate, allows for sodium to come in. Sodium is a positive ion, it comes into the cell, making the inside, instead of -70, making it less negative towards the positive direction. Make sense? So these are kind of the fundamentals that I wanted to introduce before we dive into action potentials and local potentials and how they're firing and how they're being used. Couple of review questions. So let's walk through these together. Which of the following is not part of the central nervous system? We've got nuclei, oligodendrocyte, microglia, Schwann cell, ependymal cell. Two of these or all of them are part of the central nervous system. If you guessed or answered D, the Schwann cell, you'd be correct, because the Schwann cell is actually in the periphery, right? All right, next one. Sodium potassium pumps in neurons consume an estimated 20% of all energy in your body. Why? They're required to establish resting membrane potential. They are required to maintain resting membrane potential. They require 2 ATP molecules for each round of work, 1 ATP to push 3 sodium out, and 1 ATP to pull 3 potassium in. Or I have no idea. The correct answer is, in fact, B. They are required to maintain but not establish the resting membrane potential, right? Okay, that wraps up the lecture. Just a couple of extra slides that we didn't have a chance to get to. I didn't want to rush, and I wanted to make sure that you had the opportunity to kind of feel the full setup of the introduction on nerve physiology before you launch next week into this same material in more detail. All right, thanks so much.